Welcome back to Theoretical Quantum Matter Physics, and this is the second video of DFT Practical Class lecture series where we are actually learning on how to use Quantum Espresso. So, in the previous video, that is in the first tutorial, you have already known what is a name list, what is a card, and many other things also. But what we have also known in that tutorial was that at first we have to make a convergence test, right? That K point and energy cutoff convergence. But the catch here is to make the convergence test, you have to run self-consistent field calculation. So we are back to the third point. At first we have to learn how to run a self-consistent field calculation. Okay, so let's begin. Now, to do a self-consistent field calculation or any calculation in Quantum Espresso, you need a structure, right? You need a crystal structure, and there are several sources from where you can get the crystal structure. At first, you can get some experimented crystal structure from any experimentalist. At second, you can make structures using Vesta, right, from a paper. And I already have a tutorial for that. You can check this. And also, there are several other online sources from where you can get the crystal structures. So here, in this particular video, I am going to show you some very good online sources to get the crystal structure files, right? Well, so here I have opened Chrome already. Just go to Materials Project. Now here is this website, Materials Project. Now these are the optionals. You may provide them, you may not provide them also. Okay, so just save it. Start exploring materials. Now just you can type here which material do you want. And maybe for now we can do the structural calculations for barium titanate. Okay, so let me just write PaTiO3. Okay, so that is the formula for barium titanate. It is already here. So just click it, and there are several different structures for BaTiO3, right? Here you have it. So let's say now let me do it for cubic. Okay, now let me just export this structure as CIF. Okay, here we have it. Just go there. You have the structure. Now you have to open it. Okay, so just to open with, you can do many apps. Okay, for example, look for another app on PC. Now let's say let me open it using Vesta. So let me just go to C drive. Here I have kept my Vesta. Okay, and here I have Vesta open. So this is the structure of barium titanate in cubic form. Okay, so we can also open it using Burai. So let me just do that. Just do open with and more apps. Just go to look for another app on this PC and just go to C drive where I have kept Burai, bin this. But this is for the first time only. For example, if I close this, from next time on, if I just right click, I do open with, choose another app, and Burai will be there instantly. Okay. So let me just open it. Okay, here you have Burai. It is good if you make this in crystal format. Okay, because in Vesta you will get the atomic configurations in crystal format itself, right? So just do that, and we are not going to do it Ba2 plus Ti4 plus or O2 minus. Okay, so just do. I have just double clicked here. Okay, in Ti. So just rename this as Ti, and here you have oxygens. So just click it, and other oxygens are here. So just rename these to also. So rename these also as oxygen. Okay, just deselect this, and finally we have come to barium. Just click it and rename it as barium. Okay, so it's done now. The cell is cubic, and this is the lattice parameter. Always I suggest you always to cross check this with Vesta. Okay, so I'll just go to Vesta, go to edit data and unit cell. Okay, see, lattice parameter is 4.00768 and it is cubic. So 4.007. So that is good. So Vesta is a trademark. You always have to cross check with Vesta. Okay, well, let's just go to atoms. In Vesta you have atoms also. You have the structure parameters here. For example, barium is at 0.5, 0.5, 0.5, right? And Ti at 0, 0, 0. So just check this only. 0.5, 0.5, 0.5 and 0, 0, 0. and oxygens will be by default then will be in the right positions. Okay, well, so this is the geometry. Now let's just go to SCF, but definitely after doing geometry you should go to SCF. We'll change this SCF input file in various places that I'm going to show you right now. So just Ctrl A, Ctrl C. I've just selected this whole input file and copied it. And now let's just go to maybe desktop. Let's just make a new folder and let's say I name it as test. Okay, well, so let me put it here and now take a new text document. Well, so let's rename it as BATIO3 SCF.in. Okay, so just click it, just go there. Okay, so just paste it here. Okay, now in the previous video I have told you what is a name list, what is a card. As you can see also, as we have discussed in our previous video, there are three main name lists, right? And control, and system, and electrons. So they are here, right? So calculation is a shape. Now I have told you already, right? In the previous video, what other values other than a shape you can put here. So but now we are doing a shape calculation, that is self-consistent field calculation. So we are going to put a shape here. Max second. So this defines for how much second your calculation is going to run. Always try to make it bigger. So let's say 10 to the power 8. Okay. Sometimes many relaxation calculations may take longer times. Okay. Now this pseudopotential, I have told you in previous video that if you are a beginner, it is better for you to put just a dot here. This is lattice parameter, already told in the previous video, dGauss, ECAT rho, ECAT WFC. These things I have told you in previous video. But ECAT WFC, that value is not good actually. Okay. So now let me put 70. When you are doing SCF calculation for the first time, okay, just do this 70 and this 700. Because we don't know, since we are doing it for the first time, we don't know whether it's an insulator or it's a metal. So as I have told you in the previous video that for insulator it's 8 times and for metal it's 12 times, right? So I am just keeping it 10 times here since I don't know. But for barium titanate we know it's an insulator, but for other materials you won't know actually. Okay, so let me just put 10 times here. IBRAB is 1, that's for cubic, I have told you. A nat is 5, n spin, we don't need it here, so just delete it. Okay, n type, 3 type of atoms are there. Okay, I recommend you to please go to the first tutorial to know all these things, because these basics, what they mean, I have already discussed in the previous video. Okay, so smearing, it's Gaussian. Okay, and convergence threshold, that is at what decimal point of energy the SCF iterations are going to converge. So that is 10 to the power minus 6, which is actually good. Electron max step, that is 200. I have recommended you 200 also in the previous video. Well, now this here, K points, that is 333. This is actually not good if you are doing only SCF calculation. Let me tell you a theory for that. Okay, what you should put here. Now here A is what? A is 4.00. Now what is K point convergence and how you should do it? If you want to know the real exact theory for that, please go to this video in the link. Okay, but here I am doing it only the practical, and you are going to learn some tricks here. Just do what is your A or ABC, all are 4.00 approximately, right? Now what you should multiply with A to make it 40, 10, right? If you just multiply 10 with 4, that will be 40. So keep that number here, which will make 40, this one. So just do 10, 10, 10. Here the number which I am actually putting by trick is the number which will by multiplication make A 40. So let's say you have an orthorhombic lattice where you have different A, B and C. So let's say your A is 4, B is 10 and C is, let's say 5. Okay, so what I will put then in that orthorhombic calculation will be, the K points will be 10, that is 4 into 10 is 40, 4 because that 10 into 4 is 40, and 8 because 5 into 8 is 40. So that is just a trick. Okay, so just so since it's cubic, I am just putting 10, 10, 10. Now atomic species, that is okay, that is Ti. So now this is the place for pseudopotential file. Okay, what I have already told you in the previous video, but this is not what we are going to work with. So let me go to the Quantum Espresso pseudopotential directory. Okay, here it is. You can just go to this website to get this table. So now just go to BA, that barium. Now something you need to focus here. Okay, so which pseudopotential you should take? I have already made a video on that. Here we are going to work with ultrashaft pseudopotential. Why ultrashaft? You can check here. For insulator and for non-magnetic, ultrashaft pseudopotentials are very good actually. Okay, so let me just go to USPP and PBE, scalar relativistic, right? So just do it, right click, save link as. Okay, I'll just keep it in desktop within test. Okay, so that is done. But remember, that is USPP and PBE, right? Okay. Now, let me just go back once. Let me just go to TI, and here also you cannot take PO and PBE shell with USPP. You have to take all the pseudopotentials in the same pseudopotential type and functional type. If you are taking PO and PBE shell, all three should be PO and PBE shell. Okay? Well, so we are going to find USPP and PBE type pseudopotential. Well, here it is. So just right click it, save link as, and it is here. Okay. Now let me just go back once more. Let me just go to oxygen. Well, and also here you have to find this. Okay, so this is also good. There are many different USPP and PBE. You can take any one. Okay, so let me just go back to the first one. Just right click it, save link as, and just put it here. Okay, well, so just go to that folder, just copy this name, Control C, and here we have the input file already. So for oxygen, I am going to put that. Okay, now let me just go to that folder once again. Maybe I can just do that, and let me just keep it here. Okay, now this is for barium, right? So let me just copy it, and I will just paste it here in place of barium. Okay, now for TI, just go there, just copy it, and just paste it here. Okay, so this is done. Okay, well, now that is okay. We already have the input file. So just go to file, do save as. You can do any name here. Okay, you can do SCF.in, you can do BATIO3, even you can do BT-SCF.in, or anything, any name you want. Okay, just remember the extension should be .in, and here you should select all files. Okay, otherwise it is not going to work, because Quantum Espresso does not recognize .txt format. It will recognize .in only. Okay, so now just save it. Okay, so just close it, close this, and we have this. So this is what we are going to work with. That txt file, we don't need it anymore because we already have .in. Just open it, open with more apps and notepad. Okay, we have .in file here. Okay, so let me just close this. Okay, so actually this one is not needed because we already have BT SCF, so just delete it. Another thing, we need a command to run it. Okay, how to run a Quantum Espresso input file in Windows, we have told in previous video already. But now I am going to show you some other thing also, which we are going to actually use in K-point convergence and energy cutoff convergence test. Okay, so just take another text document. Well, let me write BT. Okay, BT itself is okay for now. So the input file name is BT_SCF, right? So just do PW space less than BT_SCF, just the name of the input file .in greater than. Now you can put any name for the output file. It is not necessary actually that you have to put BT_SCF itself. For example, I can write BT, or I can also write BATIO3. Anything, you can write your name also. For example, if I write THRTCL CMP or anything .out. Remember this, the output file name and the input file name need not be in the same name. Okay, why I am actually saying this, because when we will do band structure calculation, this will create confusion. Okay, well, so let me just save it, save as. Now for this, save it as batch file. Okay, okay, make it a practice to save it in batch file and make all files here. Just save it. Okay, let me just close it now and select all of them, all the files. Let me just copy this, and now I will paste all of these where I have kept the Quantum Espresso itself. Okay, well, so the Quantum Espresso is here. Okay, now let me just paste them here. Okay, maybe I can sort by date. Okay, here are the files for barium titanate. Okay, now I will go to Windows PowerShell. Okay, so here is Windows PowerShell. So I hope you already know how to use Windows PowerShell, right? So, but let me do that also. Just if you want to go to previous directory, for example, now we are in C drive. Within C drive, there is a directory called users, and there is another directory called user within users directory, and we are in that directory. Okay, so we'll go back to C drive, cd // that is going back once. Okay, we have to go back twice. So once again //. Okay, so we are here. Now if you want to know what are the directories, what are the files that are kept in the C drive, just do ls. Okay, just put enter here. So these are the directories. So I have Burai here, Intel here, Microsoft Office, MPI, program files, and all these Vista, Windows, and all the zip files, right? So which directory I want to go in? Where are my input files? Within QE_win, right? So just do cd, that is going to our directory, QE, just put a tab here. Well, it is here, just do enter. So we have QE_win. Why tab worked? Because there is only one directory which starts with QE. Pressing tab only once will give one of the directories which starts with QE, and twice will give another directory. Now we have only one, so only one tab actually worked. Okay, well, if we again do ls, we will see that QE folder is there, right? So just do cd QE. Okay, once again I have pressed tab after writing Q. Okay, now do ls. Okay, now we are in the Quantum Espresso directory. Okay, now just run that batch file. Okay, if you see, we have the batch file here, that .bat, right? So just copy it. I mean, you don't need to copy it this time, only bt is there, but maybe several times in future we will have long names. Okay, so that's why I have copied it. So just do /, just paste that name and enter. Okay, now this code is running. So this will run for some time. Maybe I will fast forward this video. Now in the meantime, while this is running, let me explain few parts of this input file to you, which I have explained in the previous video. But since this is BATI03, this is another example, I'll just say some important things only. That IBRAB is 1 is for cubic, right? For a tetragonal orthorhombic, I have provided a whole list in the previous video. Now N@ is 5. What does it mean? It means in the unit cell of the cubic barium titanate, there are 5 atoms. This number 5 should match with this. Positional coordinates of 5 atoms should be there. If N@, that is number of atoms, were 20 here, then I would have to put coordinates of 20 total atoms here. Okay, and this N type, that is 3. What does it mean? This means 3 types of atoms are there. That is, one is Ba, one is Ti, and another is O. Okay, okay. So let me just fast forward it. Okay, so the run is now complete, and so as you can see, CQE win QE is here now. Okay, this means actually that the run is complete. Okay, so now let me just go to this directory of QE. Here you have the output file. Just open it with Notepad, and as you can see, the job is done here. Okay, and it had taken 9 minutes. Okay, well, okay. So this is how you run a self-consistent field calculation using Quantum Espresso. and you can see that PWSCF, this is here. Do you know what is this? This actually contains the wave functions of your crystal. Now, why did I say in the previous lecture that before doing any calculation, for example, before doing band structure or DOS or elastic or any other calculation, you have to perform a self-consistent field calculation, because in self-consistent field calculation, the wave functions are created. With this wave function, the further calculations will proceed after SCF. Okay, so congratulations, you have learned SCF, and now just don't forget to like and subscribe to our channel, because your like and your subscription is what that fuels our channel. Okay, well, okay, so let's continue in the next video. Well, bye for now.